now. So welcome back, YouTubers, officially for the recording. We've just learned that 6-7 does not mean anything. It's just an expression of defiance designed to annoy your parents. So that is what we've learned thus far. Let's see. What are you guys working on next? Let's see if you know.
Assessment.
Yeah, formative assessment number 3, I think. This one's on Michael to present. So yep, those are over this lecture and all the concepts. So I expect that we'll spend a decent amount of time talking about that on Tuesday. Just to remind you, how many points do you get if you do it? 3. How many points do you get if you do it badly? 3. I want you to give it a try. And I'm not keeping track of how long it takes you to answer the questions, how many tries you want to submit. I don't care if you use your notes, but ideally, it would be good to try not to. Just sit down, try to answer the questions. If you get stuck, that would be a good time to refer back to your notes to try to get unstuck. But to see how much you can recall off the top of your head, I think is a useful starting point. We were looking at how to make numbers show up in output and syntax last time. Should we jump back into that? Maybe review where we have been? Does that work? Zoomers, do we have any thoughts? Good on that? All right. So this example, predicting income from years of education and binary marital status. So just one variable at a time. The next unit will be multiple variables at a time. So we started with an empty model for pedagogical purposes largely, where I have no predictors. So this model, the purpose of it is to essentially recreate the mean and the variance of this outcome as the naive starting point where everybody's predicted outcome is the mean. E is how far off the outcome actually is from the one that's predicted by the model. And E is wrongness, error, residual, discrepancy. Those are all words that you can capture wrongness with. So we did that in Stata with the command regress, short for regression. The first table I told you can ignore, except for the one number right here. That's the variance of this variable. That means that is all the reasons why income differs across people that we don't yet know about. On average, people make $17,000. In R, the function we're using is called LM for linear model. Formula is where you actually put the model that you want to fit. So you got to tell it what data set, what the name of the variable is, and then squiggle is like the equal sign of the equation. The 1 refers to the presence of a fixed intercept. That is optional, but I always put it in my code to remind myself for reasons to be described subsequently. And we get 17 as the fixed intercept. This is an extra piece of output that I asked for from a function called supernova that creates what's known as a sums of squares table that mimics what it looks like in Stata, and here's the one that we want to pay attention to there. Then we added education, years of education as the predictor. And variance is now 162 relative to 190. Is that good or bad that it went down? Good. Yeah. So if we think of variance as unexplained differences between people, there are fewer unexplained differences after adding education. So in this model, education has a slope of 1.8. So I can look at that in the R output or the Stata output. There's the 1.8 in the R output as well. So for every additional year of education, income in thousands of dollars goes up by 1.8. So here's my estimate. How wiggly is this expected to be across repeated samples? Where do I look for that?
Standard error.
Yeah, standard error. So this is how far off the sample slope is predicted to be on average from the population slope. T comes from estimate divided by standard error. So a T of 11 is telling us that this slope is 11 standard deviations away from the null hypothesis of a slope of 0. So super unlikely to have happened if the true slope were 0. And it is significant. P-value is 0 to 16 decimal places, so regardless of what alpha you pick, we could pretty much call this significant. However, the intercept is -7. Do you remember why that happened? We do. One nod.
Repeat center.
Yeah, we didn't center. So the intercept is the expected income level for somebody with 0 years of education, which is not wrong, but it's weird. And by not wrong, I mean the model predictions would be the same regardless of whether you centered. Your R square, which means is going to mean proportion of variance explained by the model, will be the same. It's literally just this number has an impossible interpretation. So it doesn't hurt anything per se. Here's some confidence intervals. So we're going to fix it then by centering the variable by subtracting the constant.
So what
Yes,
is
please.
that 2e minus 16? It was
2e, oh, this is scientific notation. So it means essentially the minus sign means start at the decimal and then there's going to be this many zeros. Mike, can you explain this better than me? It's been a long time since I explained
Yes.
this.
So that scientific notation, forget the e. 2 times 10 to the negative 16 power. That's what that means.
Okay, forget the e. This
Oh.
means 2 times 10 to the negative 16.
You like that?
That sounds better than what I said. But I might be saying the same thing, I hope, or close.
It's actually 15 zeros because the 2 would be the
Okay.
16th place, but yeah.
0 to 15 decimal places, not 16.
I wasn't going to correct you on that.
Oh, no, you should. If I say something wrong, I absolutely should be corrected.
Okay.
Yeah, no, that's
All right.
fine.
Very good.
0 to a lot of places is the answer to that. If you don't like scientific notation, and I don't particularly, there's an option at the top of my R syntax that allows you to control how many digits of zeros are printed before it switches over. So like I have mine set to 9 or something huge like that. But that's just a display option that you can control as you wish. All right, so if we center it, so we subtract 12 so that the reference person for the model, the you are here sign for your data, if you will, is somebody with a high school degree. Now what's going to change and what's not going to change?
The intercept is going to change, but the slope will not.
Exactly. The intercept changes because we've redefined what 0 means. The previous beta 0 was for literal 0 of education. This one is now going to be for education of 12 because that's when this term would 0 out in the new variable. So we got to make the variable first. In Stata, the command is gen, stands for generate, and the new variable goes first. I always add the centering constant to the end of the name of my new variable. That way I don't have to remember what it is offhand. I can just look at my output and realize that. The name of the original variable is here, and then whatever constant you would subtract would be here. Now let me show you what I see people do frequently that will screw them up subsequently. This. TAs are nodding. What's going to happen if I run this code?
It's going to overwrite your original data.
It's going to overwrite it.
Every time.
Every time.
Every time you run it.
So that
Until
means
you
that if you
reload.
rerun it, it's going to subtract 12 again and again and again and again, and you're going to get further and further away from what the actual scale should have been. So I would not ever overwrite a variable. Just get in the habit of making a new one.
Oh, question. Would you?
Yeah, seriously.
So,
6, 7.
so after you're modifying your data, would you recommend saving a new file, or at least overwriting so you can see all the new columns and stuff for just for reference for later?
So the question was, would I save the new version of the data set with the variables that I've built?
Yes.
Okay. I would say it depends. If it is a very long, complicated process to go from a raw data set to the version that I need for an analysis, yes, because that just saves me time to have the finished version that I can just have accessible. Otherwise, no, because you can end up with 47 versions of the same data set and not have any sense as to how they differ from each other. Whereas like here, if I start with one data set in Excel format, I can't write over it from inside Stata very easily. Like that won't happen by default. And then I have code that creates different versions of data as needed. So if it's a small data set or there's not a lot of code for transformations needed, I'll just recreate it every time. If it's a big process that merges in lots of separate data sets or something to where it's its own thing, then yes, I would save the results of that. Question or comment?
This is also a helpful way to use your do file to like make notes.
Yep.
You know, like you can say like data set whatever. You never rewrite over your original data set. Ever, 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 ever. Always like save it as something else. But if you have, you can make a note to yourself and state it that I ran this code. And then I saved that, and then you can open it, because you can highlight things, right, and only run specific pieces of your code.
Yeah, you can use comments to leave yourself notes about your process and your rationale.
I do that all the time, and it's super helpful, because when you come back to it after a week
Or
of
a
being
year,
away
or 2 years.
or more, you will forget what you were thinking at the time.
Yeah.
So those comments are super helpful.
Agreed 100. And I think when you're first getting started, like I write literally what is being accomplished by the code. Like this is going to create a new variable that is centered. But once you get into it, like you will look at this and be like, oh, I know what this code is doing. But future you won't necessarily remember why you did it. Like, why did I make this variable? What was my intent? And how does this variable differ from this other variable that looks awfully similar? Like just that kind of documentation will save you. So, absolutely. And don't ever name your data set like final version, final data. You end up with like final version 12, really, really final, I mean it this time. Like as the name,
12.137.
yeah. Don't do that. There's no such thing as final. All right, so we're gonna center. It's gonna change the intercept but not the slope. So here's a question for you. My 162 variance here, we already said that was smaller than the 190 we started with, right? 190 is right here for a point of comparison. Do I know if this difference in variance is significant? Do I know that my model got significantly better relative to what I started with? This is kind of an indirect conclusion. Cough, cough, homework question. Let's think about it from a model comparison point of view. Where did we start? Go back to the empty model for a second. This, okay? So the variance of the e's is what we're talking about. In this model, the e for each person, if I sum that, square it, then sum it across people and divide by n minus 1 because we had to know what the fixed intercept is to get the e, then the variance of the e's across people is 190. Okay, that's where we started. Then we added a centered predictor of education. So this is the new part. So if we think about what happened by adding that new beta 1 slope, my E variance, my unknown reasons variance, went from 190 down to 162. So the only thing that could have caused that to happen is that new slope. That's what made the two models different. So to answer the question, did the 190 decrease significantly when it decreased to 162, meaning more than would be expected if there was really no population relationship? We would go to the significance test for that new slope, actually, which is right there. Because that's the new thing. Like nothing else happened that made it different. That new slope is what made it happen. So that's another way of looking at it, is that this p-value for the slope of education being significant, being 0 to 15 decimal places, is also a statement that 162 is significantly lower than 190. There is less E variance. In other words, we have significantly predicted income to some extent. And I think we left off about here. So I wanted to give you some examples of how you can generate model predicted outcomes for any level of predictor, regardless of where it's centered at. There is a easier way to do this in code, but I want you to understand the concept and to be able to implement it in code to start with, and then I'll show you the easier way later on. So here's 4 examples. Here's my model equation. So y hat, remember what that is in terms of vocabulary?
Predicted outcome.
Predicted outcome without the e. So y hat is everything but e. That's why in this equation here, I'm saying this is the equation for how I'm computing y hat, and e is not part of the story. So anybody who has 8 years of education would be predicted to make $6.7 thousand a year, regardless of who they are otherwise. It's a prediction of what happens on average from the regression line.
And that is essentially just saying if income was just based on education.
That's right.
Okay.
Like this is where the line goes through y at for that value of x. That's where we are on the line. And for 12 years, that's the model reference point. That's when this part would zero out and we're left with only the fixed intercept contributing to the prediction. So that is the definition of the fixed intercept as a result. It's when all the slopes would drop out because they're multiplying a predictor value of 0. For 16 years, we plug in a 4. Remember why it's 4 and not 16?
Because it's centered at 12.
Yeah, the centering. Yep, so it's 4 more than the new 0 point, and that one. So I can compute these just fine. I can do this in Excel or a calculator or whatever. What I can't do as readily is compute standard errors for this. So I might want to show the expected imprecision of these things. We have a question, let's see, from the Zoomers. Are we looking only at the education p-value? I wasn't sure if you were saying we should look at the constant p-value too. That is a great question that results from me having highlighted the wrong thing on accident. So if I go back to the R output to start with here, the constant, that's the intercept. That's the same thing as right here. That was in the empty model too. So that isn't new. We always have the constant in the model because we're allowing for the possibility that our outcome variable does not have a mean of 0. That's what the constant's for. So the change in the model variance for the residuals, this decrease in residual variance can't be due to the constant because it was already there. It has to be due to the new part, which is the slope. And I did not mean to confuse you, but I accidentally highlighted the wrong p-value when I first grabbed this, because Stata does it backwards. Stata puts the constant at the end, and every other program I've ever seen in my life puts it first. So, fun. All right, you are welcome, Zoomers. Thank you for the question. All right, predictions. So this is Stata code on top. This is our code on the bottom. I wanted to put them side by side, though, so you could see the overlap. Let me get the equations on here so I can fit the whole thing. There we go. So lincom is a Stata command. It is known as a post-estimation command because it is using the results you've already obtained to generate new results. Lincom stands for linear combination, and it is going to retain the values of your fixed effects and do math on them. So let me walk you through like one example here. The first one, underscore const times 1. That's this. So when Stata reads underscore const, it says, oh, they're talking about the fixed intercept. What was that again? Oh yeah, the model said it was 14. Let's plug that value in. So whatever the fixed intercept became is then going to be stored in memory and part of this, this new value that it's computing. Education 12 then refers to the beta 1 slope that was estimated for that predictor. So this command right here is doing this math for you without you having to input the particular slope and intercept coefficients that your model found. Like it would work for any model for any data. The only thing you'd have to change is what the name of the variable is that you want the prediction for and the value that you want the prediction for. So these words refer to their estimated fixed effects in these models. And the results then would generate little tables like this, where here's the first one, for instance. There's the predicted value of 6.7. That's exactly what my calculator said, but it also comes with a standard error and it gives you a hypothesis test in case you care whether this person's income is different than 0. Okay. Stata folks, how is that sitting? The words refer to the fixed effects as estimated in the model. That's the key to following this. Yes?
Do you have to have the 1 with the multiplication by the constant?
You do not. So this times 1 is unnecessary from a programming point of view. The reason that I put it in is for comparability with the same code in R, in which you do need the 1. Yep. So the fixed intercept multiplies an implicit variable that's just a column of 1s so that it gets contributed to everyone's score. Okay. So are we okay with this much?
Besides the 1 does mean the fixed effect, the first fixed effect.
So the 1 is just referring to the fact that the variable that is multiplying the constant is just a column of 1s. It's an acknowledgement of that because I'm trying to make the code look as similar as possible to what it would needs to be in R. But you don't need to type times 1 because that doesn't do anything.
Yeah, I mean, just like in the R and also that it's both 1 there.
Can you say that one more time, please?
I just mean that 1 is in the R too, and you said that should be there
Yes.
always. And I just mean, is that 1 always put 1, or I need to change other numbers too?
You always have to put something, but it doesn't always have to be 1. It depends on what you're trying to estimate.
Okay.
Yes. Essentially, in Stata, when you are building a linear model, right, you need to tell it what to do here, what to do here. Anything you leave out is assumed to be 0. R doesn't have that kind of default. So this is another example right here. In the second lincom, I asked for the prediction for someone with a 12, which would be 0. Like, I don't have to type that. I just did it for parallel structure. It's just the constant. And actually, this entire line would not be necessary because I already have this as my fixed intercept. I was just trying to show the pattern. Now, our folks, this is a little more involved. If we go up to the R outputs for your coefficients, I've got 2 rows right here. The first one is always going to be the fixed intercept. The second row is the first predictor slope that you asked for, then the next one, then the next one, then the next one. What is happening in this little piece of code right here? So this is a function called GLHT, General Linear Hypothesis Test, is what that stands for. It wants to know what model results to pull from. So it is going to do math on output that you've already created. We're building a linear function, is what that stands for, and we're combining rows together so that we end up with 1 table rather than 4 tables. So it's just a printing thing. In quotes here, I am labeling what the value is that I'm trying to generate. So this C1 comma -4, for instance, you have to have something in each spot that goes with the number of rows that you have in your fixed effects. So it's like spots go with rows, just transposed. So what this is saying is, okay, go into my model output. I would like 1 fixed intercept of 14, please. And then I would like you to add to it -4 times the next fixed effect, which is the slope of 1.82 for education. So these values are the multipliers that go into your equation in the spots, in order of the outputs. They're the multipliers. So the 1 means give me an intercept. The -4 means give me a slope and give it to me for somebody with an education of 8. Then printing a summary of what I found and asking for confidence intervals of that summary as well. So Stata separates these out as little tables right here. In R, it spits it out as 1 table because of the way that I wrote the code. So then those are the 4 predictions, their standard errors, and their hypothesis tests as well. So here's an example. I believe I have it set to 9 decimal places before scientific notation kicks in, so this one has a bunch of zeros, but the rest of them don't. All right. So I read an article from the Chronicle of Higher Education this morning that said I should not say, do you have any questions? I should say, what questions do you have? So I'm going to ask you that. What questions do you have? Zoomers play along too.
May I comment on that article?
Sure.
I switched that up for like a couple of terms and I had no difference in the number of questions I received.
It didn't work?
It didn't work.
Well, the focus of the
Just ended up with a weird sample though.
Yeah.
It was convenient samples.
well, the focus of the article was like for those of you who teach lecture classes, like what are some little things you can do to make students more engaged? Because like switching how you ask that question is a very low level, like, oh, I can do that. You know.
Can you talk through the reasoning behind the R code again?
Yep. So the big picture, what we are doing is using the results to create predicted outcomes for different kinds of people. I have 4 examples of different values that you would want predictions for. The values inside these little C functions here are the same numbers that are in the parentheses here that serve as multipliers that fill in the values of the predictors that you want the predicted outcome for. Predicted outcome for what kind of person. So regardless of who you are, everybody gets a fixed intercept to contribute to their predicted outcome. So the ones here are explicit in the way I'm writing them, and in here they're sort of implicit here. But we start off with that. Then the value here is the value of the predictor that you want the outcome for. So this means I would like a predicted outcome for somebody with -4 education, which means 8 years. So it's going to take -4, and then it's going to secretly multiply it by 1.82 that it's storing in memory, and then it's going to give me this result. So it knows what the answers are for what your fixed effect estimates were found to be, and this is telling it what value to multiply each of those estimates with to create a linear combination.
What are the print functions doing?
Here,
Yeah, like that one and then the first 2.
these are titles and notes that I want copied to the output screen.
Okay.
And if you work with the console, like the default RStudio, all your comments, all your commands, everything gets corrected to the
Yeah.
console, so you don't have to worry about this. But when I build examples, I output them to a separate text file so that folks can
Yep.
open that without having to need R. And inside that text file, it doesn't print the comments.
Okay.
So I turned comments into these print titles so that they'd show up in that file.
Okay.
That's all.
So yeah, to get your output, you don't have to do those prints like
That's correct.
within the. Okay.
Yep, so this is just me trying to
Gotcha.
say what's happening down with this code.
Perfect. Yeah. I was so confused.
Yep, no, it takes like way extra code to do things in R relative to Stata, and it's super annoying. But that's just where we are with life.
Okay.
Yep, the prints are optional. This is saving the results to an object that is also optional. The reason I had to do that is because I also wanted to request confidence intervals, and to do that it needed to be an object already. So essentially I'm creating an object that has the results I want. I'm then asking for a summary of that object to be printed, and then I'm feeding that object into a confidence interval function to get those as well. A lot of steps, unfortunately. So then here are the results from R. This is just the GLHT part, the summary function, and then the confidence intervals portion adds those two, if you'd like confidence intervals for those as well. Okay, different question then, unless there's other questions. Questions from the Zoomers, yay! Can you confirm what does C stand for? In R, this is just concatenate, like stick together, or combine. You want to say another one?
I think that C is for column.
Oh, in this case, yes.
Because you have a column of 1 -4, and technically you're multiplying this way, which we won't talk about matrix multiplication, but yes.
Yeah, so this pattern of C and then stuff in parentheses shows up in R all the time. I think of it as any time that you need to send a list of things rather than one thing, then you need the C to like trap it into one thing. So whatever it stands for, yeah. It's a way to like generate a series of values all in one fell swoop like this. And we will see this in C functions. So like here's another one in the descriptive statistics, for instance. Scroll back up here. Yeah. So in R, for instance, the describe function is looking for a variable to summarize. Because I wanted to summarize 3, I have this C function that like stacks them together and then sends that list to the command. So combine, column, concatenate, something. Chartreuse. There's a crossover with the other class. Yes, confused with constant. No, that is the one thing it doesn't stand for, is constant. Can confirm. We need more letters. 26 is too few for what we're doing here. We need some more. That's why we borrow from Greek letters. Okay, different question then, unless there's more questions. That was another thing the article said, it was to pause longer. Okay, so we've established education is significantly related to income. As education goes up, what happens to income? Up or down? Up, because it's positive. Is this slope within expected territory, if there really is no true slope, or is it in unexpected territory? Unexpected, and what do I look at to ascertain that? What am I asking? Expected versus unexpected. Vocabulary word starts with an S.
Significance.
Yeah, significance. So what am I looking for?
Really, you're looking at your p-value, but you could potentially get an idea from your t-score or your confidence
Yep.
interval.
Yep, so the p-value is the direct answer. If p is less than the alpha you've chosen, then we would say this result is significant, reject the null, sufficiently unexpected if the true value were 0. Would happen less than 5% of the time. But you're right, that we would expect what value of t typically corresponds? Yeah, 2-ish. If t is greater in absolute value than 2-ish, that's usually about where 0.05 is. And I could also say the fact that this confidence interval does not include 0 also means that it's in unexpected territory. So there's a couple different ways. Well, significance is a function in part of sample size, because the more people you have, the narrower the boundaries are for where unexpected starts. So how can I get a sense as to how strong this relationship is, like absolutely? 1.82 is in units, right? I have to know it's in thousands of dollars and years of education. Is this a lot? So significance just means not 0. It doesn't really answer the question, how related are these two things? For that, we need to transform the slope into a metric by which we know what the answer is, regardless of the scales of the variables, an effect size, if you will. Is that a term you've heard before? Effect size, maybe? A little bit? Can you think of a letter that goes with effect size? Did you learn any letters for that? I can think of 2 or 3. No? This new topic then.
Is it not D?
D's one. Yeah, Cohen's D, as they usually call it. And there's a whole family of related things. There's like Hedges G and Delta's Delta, or I don't know. It's not my area. There's a lot of them though. There's another family though that's not standardized mean difference. It's in a correlation metric. What letter goes with that? And it's not C. That's also not what C stands for in the R code. It's R. Yeah. So we're gonna work with a couple different versions of effect sizes in this class. Here's your first one. Pearson correlation. It turns out that what we just did, sticking a quantitative predictor of a quantitative outcome into a regression model, is equivalent to fitting a Pearson correlation for those two variables. If X predicts Y, then Y predicts X. So we're going to ask for, to get this information, I'll show you a couple different ways. Yes, D and R are very good Zoomers. In Stata, we're going to ask for what is known as a standardized solution for the regression. This is used to transform the variables into a common metric at all the X's and the Y in mean 0, standard deviation 1, a z-score, in other words. That way, all the slopes are on the same scale, and we can look at their relative differences and make conclusions about which are relatively more important. It also tells us how big the relationships are in a metric where we readily know what it means. So in the standardized solution, here's the magic word that gets you that. Beta. Greek letters. So comma and then beta. Here's the results that we had before. And then clear at the end here. Like they put beta in the naughty corner, like all by itself over here for some reason. I don't know what's up with that. The beta for education is 0.38. That is a standardized slope. In standardized units, for every standard deviation increase in education, standardized income goes up by 0.38. So what's the most this could be? If these variables were perfectly related, what number would this be? What's the highest correlation can be? 1, yeah. And since it's a positive relationship, we know it's going to be a positive correlation, but a correlation of -1 would be equally perfect, just in the opposite direction. So this one's 0.38. So that gives us a sense as to how related these things are. Decent related, but it's not like guaranteed if you get one more year of education, you're going to make more money. 6, 7. 0.38 is sort of a medium, I would say. And different authors are going to have different labels for what small, medium, big is. There's an article on your reading list that says don't do that. Just give them the number and let them come up with their own label. But 0.38 tells me, like, on a scale from 0 to 1, how strong this relationship is. And I don't even need to know whether it's pounds, dollars, years, inches, or whatever. I can look at a 0.38 and know what to do with that. That's the beauty of effect sizes. In R, there's a little package I found that just spits that out. lm.beta. So you feed the model into that, and it comes back with these two things right here. Now note this, NA. In life, that stands for not applicable. In R, that sometimes stands for missing data. But Stata returned that same number, the standardized estimate for the intercept. R called it NA. You know what Stata called it? Dot. So this is what the intercept will always be. By definition, in a standardized solution, the intercept is 0. Because the only job for the intercept in an unstandardized solution is to adjust for mean differences between x and y. If x has a mean of 0 and so does y, there's no mean differences, there's no adjustment, and you don't need it, so it's a dot. Cough, cough, homework question. In general, if you see NA or dot, it means something either broke or it's not a thing. Depends on the context. All right. Anything you want to ask about or clarify? So standardized slope of 0.38. That's what we just learned. Question.
Would this be the same if you ran it for your original model of education that wasn't centered?
Yes, it would.
And so the only thing that would look different, like in the code for R, is that name would be different.
That's right.
Okay.
So if I asked for the standardized solution for the not 12 version, I would get the exact same answer back. Which should be reassuring, right? Because you shouldn't be able to mess with your results by subtracting 12. Like you shouldn't have that kind of control. It's just a rescaling. And so this is rescaling it further into a z-score metric where mean is 0 and standard deviation is 1. Do you want to see another model? Like 6, 7? 7, 8? No?
7, 8, 9?
I know, I was going to do that joke next.
Sorry.
Why was 6 afraid of 7? Because 7, 8, 9. No?
Good.
It's good. Yeah, thank you. Yeah, I once had like a 5-year-old try to one-up me on that joke, and he's like, "Why was 3 afraid of 4? Because 4, 5, 6." I'm like, didn't work, kid. Thanks for playing, though. Yeah, no. But guess what? The same technology can be used to examine binary predictors. So welcome to what other folks would call a 2-sample t-test or an independent samples t-test that I still call a general linear model. So Mary 01 here, that's my next variable. That refers to a variable in which unmarried people are coded as 0, married people are coded as 1. Binary variables are agnostic as to whether they are considered ordinal or nominal, because there's only 2 categories, there's only 1 difference. So even though this is a kind variable, a categorical variable, we can still treat it as quantitative, because the slope for this model still tells us the effect on y for a 1-unit difference in x. But in this context, a 1-unit difference in x is going from the 0 group to the 1 group. So it's the same idea, even though we're talking about groups. So first things first, I need to recode my group so that 0 means something. Here is one way to do it that would generalize to more than 2 groups, which is why I wrote it this way. First in Stata, then in R. So I am first making a brand new empty column. I am naming that empty column Mary 01. And so here's the dot. That means missing. Then I am systematically writing over the values. If Mary, the original column, equal 1. Zoom in here so you can see that. That's not a typo. This is an equality condition. So if the old variable is 1, then keep this, or excuse me, make these values that we're missing into zeros. If the old variable was 2, make the new variable into a 1. So we are recoding to shift them over by 1. I could have just subtracted 1 and that would have the same result, but this way would generalize to more cases. Now why would I want to do that? If I left my variable as coded 1 and 2, would that cause any problems? Would that cause any problems to leave the 1-2 version in the model as a predictor? Say it again?
It shouldn't?
It shouldn't, no. There'd be one weirdness though. The intercept. Who's the intercept for? A 0 person who doesn't exist. There's only 1 people and 2 people. So the intercept would be for not a person in our sample, and that's some weirdness, but it doesn't make it wrong. It just extends the regression line further than we intended. Yes?
Does the order of those 2 statements make a difference?
I do not believe they should, because there's no like if else that would cause some filtering to happen. It's processing all the rows each time. If I had a giant data set with a lot more conditions, I would probably set it up like
Or
if this, then this, if this, then this.
overwriting, like you said, not to do.
Yes.
That'd make a giant difference, because then everything would be a 1.
Yeah, then you would be in trouble. Like if you overwrote your column, then you'd end up with this loop that would never end. But yes, I'm making a new column in this one. Yeah. Okay. So then in the code, I'm swapping out education. We're not looking at that anymore, putting that in for marital status. Now I'm doing some extra pieces here. Matrix. This command in Stata, this is actually something new for my toolkit, relatively speaking. I am saving the results to an internal Stata object in the same way that our results are stored to an object. because then I can access that object and make it do math and things on it. So there's one command that I need to do that I couldn't figure out how to do otherwise, and this way worked. So I will show you that in just a minute, but I am storing the results for my future reference a couple pages from now. 180. I have that number bolded right here in Stata output. Down here in R output, here's the same 180. I forgot to bold it there. Here is the corresponding R code to make new variables. Start with an NA, means set it to missing. And then this little inside function here essentially does the if the original Mary was 1, then the outside part makes it go to 0. If the original Mary was 2, then the new variable goes to 1. So it's the same idea, just having more extensive code to do that. The 180, what is that?
Residual.
Residual what? One more word.
Error.
One more word. Residual error.
I was just gonna say error.
I need to know one more word that starts with a V.
Variance.
Hey, there you go. Residual error, unexplained variance. Yes. So this is the E variance left over after allowing income to be predicted from binary marital status. Now, it's down from 190. 180 is less, right? Is it significantly less? We can check it out. Here's our results. We'll go through the R version here. Fixed intercept is 14.445. Who is that the predicted income in thousands of dollars for?
Unmarried.
Unmarried people. How do you know that?
Because it's the intercept, so it's technically an x of 0.
Yep, because that's when, in my coding scheme, x is 0 for people who had a 1 on the original variable indicating they are unmarried. So my coding scheme dictates who the reference group is. It's a choice. But knowing who the x of 0 is the first step here. Very good. So then I lost it. Here we go. So unmarried people are expected to make $14.445 thousand. Married people, and this is individual income, by the way. What happens if you're married?
Goes up by $6,224.
Yeah, married people make more money by 6,000 and some odd dollars. What if I switched the coding of my groups? What if I made married people the 0? Then what would my slope be?
Negative.
Yeah, if I switched who the 1 and 0 is. So right now 14 is the 0, and I'm going 6 up to get to the 1. If I switch who's who, I'd have to have 6 to come back down. So the slope would be backwards. So in your homework, for the next homework as well as, which is available by the way, homework 2, is that where we're at? Yeah. Homework 2 is open, TAs have done it, it's due in like 10 days or something. Yeah, that sounds right. I have several questions that say like which group is different from which group. The answer is always how the 1 group differs from the 0 group, and it has to be stated that way because of the directionality. You can't just say the groups differ by 6 because that's unclear who's higher. So married respondents are predicted to make $6.2 thousand more than unmarried respondents, is how I would say that. If I were to have done a 2-sample t-test, did you learn that? Introstat once upon a time? Maybe? Independent samples t-test? Any other synonyms they would know? No? Well, if you had learned it that way, here's your T. That t-test statistic for the difference between 2 means is the t-test statistic for the slope. That differentiates the 2 means. It is the same thing. The fact that this slope is significant to many decimal places indicates that this variance of 180 is significantly less than this variance of 190, meaning we did a good job. We explained something. Now in this case, we have one predicted outcome, right? We know the outcome for the 0 group. What would be the other possible outcome we'd be interested in?
The 1 group.
The 1 group. right? That's the list. That's all the possibilities. So I'm going to do the same process in terms of asking for predicted outcomes, but the list is shorter. So in R, for instance, I have just 1, 0 for the prediction for the 0 group. Don't technically need that. And then 1, 1 for the prediction for the 1 group. Put in 1 for the fixed intercept, put in 1 for group. The corresponding Stata code has 2 lincomps that do the same thing. And there we are. So 14 and 20. Difference of about 6, just like we would expect. One last thing, effect size. For mean difference kinds of analyses, so when you have grouping predictors and you want to know how different their means are, R is not as intuitive as an effect size as the D family. The difference is in how we're going to compute it. So Cohen's D is often computed from the raw data, using the difference of the 2 sample means and some kind of pooled standard deviation or reference standard deviation. In this class, I'm going to not use the raw data, but instead use the model to compute effect sizes. That way, when we have a more complex model with more stuff in it, we can get corresponding effect sizes that go with the model and not the data. So there is a handy-dandy formula, it's a little one, that you can use to get a Cohen's D effect size, which is a standardized mean difference, so it's a mean difference in standard deviation units between 2 groups, from the t-test statistic that goes with that slope. So based on the output, 2 times t was 6.25. There is, where did it go? Up here. There it is, there's my t-test. Divided by the square root of denominator degrees of freedom, that's sample size minus the number of fixed effects. And that's my D. So another way of talking about this is that yes, people who are married have significantly higher income by $6,000. The standardized mean difference for that is 0.46. So married people are about a half a standard deviation higher in income than unmarried people. That's an effect size that would go with that. Now, if on your homework you want to try to compute this D yourself with your calculator, be my guest. However, I want to show you how to do it with the code. And this will be, I think, the last thing that we have a chance to talk about today. So I'm on page 9 of 11. So first, let's do it in Stata. Stata is a calculator. I can make it do math by typing in numbers. So if you type display, it means, hey, put this in the output. I typed in the equation, 2 times t divided by the square root of denominator degrees of freedom, and that's my number. Now, while this is nice and simple, it's not generalizable. Like, if you wanted to use this code, you'd have to change 2 of the numbers. And you'll note that this is only printed to 2 digits of precision, and that could make a difference potentially in some applications of very small numbers. So this is where we're going to do what we can do in R and access saved results. So back at the very beginning here, I had mentioned that we saved the Stata results to a table. So matrix is the command that's going to save the results of the analysis that you just ran to an object of a name that you give it. So I call this Mary results, because that's what it is. I'm then going to ask it to print that saved result table. So matrix list is basically a print function for the object that I've named Mary results, and here's what I get back. So this will help me figure out how to tell it to do the math that I want it to do. So this is a restating of the fixed effects table, where the first row is the estimate. So this is the estimate for the slope for marital. This is the fixed intercept. Then the standard errors, then the t's, then the p's, and so on. This is the number I want, right there. So I'm going to make it do math using that internally stored number, as well as this internally stored number for degrees of freedom. So now my equation references those spots in that table. So 2 times t is what the numerator is trying to do. That is, go into this table and row 3, column 1. Row 3, column 1. So it's going to go into that stored object and grab whatever number is there. It's then going to go into the other stored object and grab that number. Question?
Should that be 3,7?
Yes, it should. Typo.
No, it should be 7,1.
Shouldn't it be 7,1?
Or 7,1, sorry.
Oh, let's do this, class. I screwed this up on purpose so we could have this live discussion. The Chronicle recommended that too. Screw up your slides and let your students correct you. What should this be?
7,1.
Row 7.
Yeah, row 7, column 1. Nailed it! Otherwise known as a copy and paste error. So yes, thank you for catching that. And I'll put that over for good measure. So then the name would be the only thing that you have to necessarily change, but you have to try to figure out in the table where the stuff is that you want. That can be the tricky part sometimes. But this is a more generalizable technique that will give you more precision in what you're computing. Question?
So this output is not changing in length, so that we don't have to worry about the 3s and 7s changing for this function.
Yeah, so these tables, as near as I've found, always have the same number of rows, and it's always in the same order. It's the columns that are model dependent. What I've learned, though, is that the fixed intercept is always the last one, because that's how it's listed in the output. So it's like
So
it
you-
takes
so-
the rows and then
And they're usually listed the same way.
the same order.
However it is listed in your output, that's the order of the rows.
Yeah, rows of output correspond to columns of this table for reasons that are unclear why they had to switch it, but that's just how it works. So the point of the story is what I'm doing by brute force here, I'm asking Stata to go in and find these numbers and do it for me here, so that I don't have to keep track of what the exact numbers are, and it will do it to greater precision. In R, it's a calculator too. So if you want to do it the lazy way, you just literally type out what you want for the formula. But here's how we can do it the less lazy way. First thing is to figure out where the stored objects are that we need, like the t-test. And in this case, it's in the summary. Scrolling back up here. This table right here, I want that number. So I need the third column. So I'm first selecting the two T columns, and then within this table, I want row 2, column 1. So that is the sub-bracket thing right here within this new table. It's a very convoluted thing. There's probably a better way to do it. But in R, you just have to find where the object is. And here's what it looks like when you click on the object. It tells you where all the stuff is. And the way that I approach is just to look for the number, honestly, that I'm interested in and try to find it in here somewhere and then drill down to figure out how to get to it. So this part can be quite tricky. I'm not expecting you to have to figure that out on your own. I've done most of it for you. So like in your homework, you should be able to repurpose this code exactly. You just need to change what you call the name of your model. And then that's going to compute it to greater precision than just doing that. And that's it. Yay! We didn't finish Unit 2, but we did finish Example 2. Which means that you can finish Homework 2, because you get to do this. Yeah. So your Homework 2 will follow this example fairly closely. You will have one quantitative predictor. You will be asked to center it and put it in an equation, interpret the output. You will have a binary predictor, and you'll get the chance to practice that as well. And here is what a write-up would look like for these analyses. I'm writing it up from the perspective of a general linear model, but at the very end, I have what it would look like if you reported it as a 2-sample t-test instead. More generally, if you want correlations among your variables, in case you don't know how to do that, I have some bonus material, so to speak. In Stata, the command is pwcore for pairwise correlation. These are the 3 variables that were in our analysis. So note the Pearson correlation of 0.38 is exactly the standardized slope from our results of our regression model, not a coincidence. This correlation of 0.225 would be between binary marital status and income, We computed a D effect size instead, but this would be the R version. And then we also get the correlation between the two variables. And so these two predictors are not very well related. I asked for, let's see here, this is Stata. I asked for confidence intervals, so you can get that. That is an add-on in Stata called CI2 that I found to do that. Question?
What are the two roles for the Mary in the other education?
These are p-values.
Those are the p-values.
Yep, so this table prints correlations, and then it has the p-values underneath it.
Is that because you did comma sig?
Yep, that's what the sig does, is add that.
So that is what gives you the p-value.
Significance.
Yep. Yep, so if you don't have that, it'll just be the correlations, which can be more convenient for reporting purposes to do it that way. Yep, so for instance, if this correlation of 0.05 has a p-value of 0.16 something, yeah, it's expected. We would say that correlation is non-significantly positive, that if the true relationship between education and marital status were 0, we would see a correlation as big as 0.05 about 16% of the time. So 0.05 is not different than 0 enough for us to say that it's unexpected. That's what that would be. In R, there's a core function, by the way, that will do correlations. There's a couple other ones too, but this is one that I've used before because it provides p-values in a nice little table. So in R, you get a table of correlations and then you get a table of p-values. And here's a function called core test that I found that will do confidence intervals as well if you want those. So that way, you can always get correlations among your quantitative variables. Ta-da! Huzzah! Yeah, ta-da, huzzah. And now Zoom is telling me that my internet connection is unstable, but I'm at work. I thought that was only allowed to happen at home. Is anyone else's internet connection unstable? I don't know. All right, 308. We still have yet to talk about next week effect size, sample size, and power, but I kind of figured that would be the case. So we'll save that topic for then. All right, anything else we should chat about before we call it a week? No? Okay, what are you going to do next then?
Formative assessment 2.
Yeah.
3.
3, yeah. Formative assessment 3 in Icon, and you can start working on homework 2 if you wish. All right, let us know if you need anything. Thanks for being here. Bye for now. 6-7. And I promise I'll leave that joke in this week.